Chapter 2: Physical Laws and Properties. The laws of science, as we know them at present, contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is that these values of these numbers seem to have been finely adjusted to make possible the development of life. Stephen Hawking, physicist and cosmologist. Experiments and observations. Throughout most of history, human beings only had the 5 physical senses: touch, sight, sound, smell, and taste, to observe, measure, and study the world and universe around them. New scientific tools, such as electron microscopes, sound analysis equipment, and powerful telescopes, have greatly enhanced our physical senses, especially those of vision and hearing. Previously unknown matter and energy, such as subatomic particles, example, electrons, neutrons, and protons, and non-visible light energy, example, ultraviolet light and infrared light, can now be studied. Recently developed equipment has made it possible to analyze light and sound energy in great detail. What was previously undetectable has been exposed in a form that our limited senses of sight and sound can use. Large amounts of scientific data are now available, and we can study previously unknown aspects of reality. Over the last few hundred years, and particularly during the last few decades, scientific knowledge in the field of physics, astronomy, chemistry, and biology has grown tremendously. Recent discoveries provide compelling evidence that there is something special about the way that the physical laws and properties of the universe work together. As many popular television shows and movies have demonstrated, evidence such as a fingerprint can enable a judge or jury to determine who was present and what took place at an earlier time. Another valuable piece of evidence sometimes found is a molecule that contains a unique genetic code for each human being. This fascinating genetic material, deoxyribonucleic acid, or DNA, is described in Chapter 4. Data from physics, astronomy, chemistry, and biology reveals fundamental truths about our universe, despite none of us having been there at the beginning to witness events as they happened. With sufficient quality and quantity of evidence, there is not always a need for eyewitness evidence. There are 2 primary types of scientific evidence: experimental and observational. An acceptable theory of reality must be supported by experimental and/or observational evidence. It must be consistent with all available relevant evidence. To ensure a reliable result, evidence must not be discarded or disregarded unless it is shown to be either invalid or not relevant. Until the last few decades, studies of the properties and makeup of the universe had primarily made use of experimental evidence from physics and chemistry obtained from repeatable experiments done under controlled conditions. For example, a simple repeatable chemistry experiment can test the theory that cinnamon oil will kill bacteria. Cinnamon chewing gum, which contains cinnamon oil, can be used to test this theory. Test subjects swab their mouths and place the swab on a petri dish. This is the control used to measure the number of bacteria in their mouth before they use the gum. After chewing the gum for 10 minutes, they swab their mouth again and place the swab on a new petri dish. After incubating for 24 hours, the bacteria are counted using a microscope to determine the effect of chewing the gum. For further confirmation, test subjects can repeat the test with chewing gum containing no cinnamon oil. Several recent studies have shown that, at concentrations of even 10% or less, cinnamon oil is effective against Staphylococcus, E. coli, and several other strains of bacteria. A well-known repeatable physics experiment is the famous Leaning Tower of Pisa experiment, purported to have been performed by the famous Italian scientist Galileo Galilei, born 1564, died 1642, in the late 16th century. This experiment shows that 2 spheres of different weights simultaneously dropped from a tower, if not appreciably affected by air resistance, will arrive at the base of the tower at the same time, proving that their time of descent is independent of their weight. Prior to the 16th century, people had assumed that heavier objects would fall faster than lighter objects. This may be because common lightweight objects are significantly affected by air resistance. A well-known idiom, light as a feather, leads to what seems like a common-sense conclusion that lightweight objects fall slower than heavier objects. The second common type of scientific evidence is observational evidence. There has been a recent explosion in the quality and quantity of observational data pertaining to the universe. This is primarily due to advancements in astrophysical instruments for observation. With the deployment into Earth's orbit of equipment such as the Hubble Space Telescope and the Chandra X-ray Observatory, much about the universe has come into focus, literally as well as figuratively. In the early 17th century, Galileo Galilei constructed a telescope powerful enough to show that the band of light in the sky, now known as the Milky Way, is composed of individual stars. Up until the 20th century, most scientists believed that the entire universe consisted of the Milky Way galaxy. In the 1920s, observations by the American astronomer Edwin Hubble proved the existence of galaxies outside our own Milky Way. The largest telescope in the world in 1920 was at the Mount Wilson Observatory in California, where Hubble worked. Hubble's observations there showed that objects previously thought to be clouds of dust and gas were entire galaxies separate from the Milky Way galaxy. The composition of the universe. Experimental and observational data has shown that the universe consists of matter along with various forms of energy. The material that makes up any physical object or substance is known as matter. All physical objects or substances consist of combinations of the building blocks of matter known as atoms. Any group of two or more atoms bound together is known as a molecule. Atoms, like the familiar building blocks made by Lego, trademark, can be joined together to produce complex structures substantially larger than themselves. These structures can be broken down into their component parts, but are not of much use unless combined. Energy in the universe includes electromagnetic energy, the most familiar type being visible light, thermal or heat energy, and the mechanical energy of moving objects. The physical laws and the properties of this energy and matter in the universe are such that abundant galaxies, stars, planets, and various forms of life not only exist, but persist over time. One obvious property of the universe is that, due to the nature of gravity, everything exists in a three-dimensional space. In their book, The Grand Design, Stephen Hawking and Leonard Mlodinow explain why. Quote, "According to the laws of gravity, it is only in three dimensions that stable elliptical orbits are possible. In any but three dimensions, even a small disturbance, such as that produced by the pull of other planets, would send a planet off its circular orbit and cause it to spiral either into or away from the sun. For the Earth and other planets to even exist, the universe must have three and only three dimensions." 4 fundamental interactions. One remarkable aspect of the universe is the precise way that matter and energy interact to produce stable elements, compounds, and much larger objects such as stars and planets. The stability of matter is the reason that the universe is not an empty, lifeless void. There are only 4 known ways that matter and energy in the universe interact. These 4 fundamental forces, or interactions, must be precisely balanced to maintain the stability of matter in the universe. 1. The force of gravity. 2. The electromagnetic force. 3. The strong nuclear force. And 4. The weak nuclear force. The force of gravity is the most familiar example of a fundamental force. Through the effects of gravity, every object attracts every other object. The magnitude of the gravitational force between two objects depends on the mass of each object and their proximity to each other. Mass is a measure of the amount of material that an object contains. For example, when a baseball sails through the air after being hit by a bat, the effect of gravity is seen as the ball falls back to Earth. The force, in this case, exists between one relatively small object, the baseball, and a considerably larger object, the Earth. Regardless of the size of any two objects, if the mass of one of the two objects is doubled, the force of attraction will be doubled. The magnitude of the force also becomes much stronger when the objects come close to each other. The force of gravity becomes very substantial for objects with large masses, such as a star or planet. In a 1687 publication called Mathematical Principles of Natural Philosophy, English mathematician and physicist Isaac Newton, born 1642, died 1726, described a formula for calculating the force of gravity. Newton related the force of attraction between two objects to their masses and distance apart. As with other fundamental physical laws, Newton's equation included a physical constant, the universal gravitational constant, or g, that can be measured through observation or experimentation. The size of this gravitational constant is such that the force of gravity is not too large or too small, thus ensuring the stability of planets in orbit within our solar system. The effect of gravity is a significant factor in the interaction of large objects such as stars and planets. Fortunately, the force of gravity is much weaker than the other fundamental forces. For as astrophysicist Martin Rees explains in Just Six Numbers, The Deep Forces That Shape the Universe, quote, "It is only because it is weak compared with the other forces that large and long-lived structures can exist." The electromagnetic force generates a force between any particles that each have an electric charge. It can be either attractive or repulsive. It gives rise to magnetism, which is the force that acts between moving charged particles. This force holds atoms together. Atoms consist of a combination of protons, neutrons, and electrons. Electrons are subatomic particles with a negative electric charge. Protons are subatomic particles with a positive electric charge. Protons have a mass more than 1,000 times larger than electrons. Yet a proton is so small that the dot at the end of this sentence holds more protons than the number of seconds contained in 500,000 years. Neutrons are subatomic particles similar in size to protons, but with no net electrical charge. Material in the physical world is composed of chemical elements. A full list of these chemical elements is shown in the periodic table of elements found in every high school chemistry classroom. Their structure and behavior are dependent on the properties of the electromagnetic force. An atom of each chemical element can be visualized as being composed of protons and neutrons packed into the central nucleus of the atom, along with one or more electrons separated from the nucleus. Each chemical element can be identified by the number of protons in its nucleus. Due to electromagnetic force, two positively charged particles, example protons, will repel one another. Similarly, two negatively charged particles, example electrons, will repel one another. However, a positively charged particle will attract a negatively charged particle. The force from these electric charges is just right to make possible the stability of the chemical elements. Fewer than 90 naturally occurring stable chemical elements exist. Unstable elements occur only in small amounts that quickly decay into other elements along with byproducts such as protons, neutrons, and electromagnetic energy. An atom of each chemical element shown in the periodic table contains a particular number of protons in the nucleus. However, the number of neutrons in the nucleus may vary. These different varieties of an element are known as isotopes. For example, although all carbon atoms have 6 protons, the carbon-12 isotope has 6 neutrons, whereas the carbon-14 isotope has 2 additional neutrons in the nucleus. As a result, the carbon-14 atom is heavier than the carbon-12 atom. Isotopes are important because they are involved in the nuclear fusion reactions as described later in this chapter that produce energy from the sun. Different from these chemical elements, but no less important, is electromagnetic energy in the form of visible and non-visible light. As with atoms, the characteristics of electromagnetic energy depend fundamentally on the qualities of the electromagnetic force. Types of electromagnetic energy include ultraviolet radiation, visible light, microwaves, radio waves, infrared radiation, gamma rays, and X-rays. Electromagnetic energy is present everywhere and influences every aspect of our lives. We experience the effect of electromagnetism when we are suddenly awakened during a lightning storm, or when we feel the tingling sensation from static electricity. Magnetism has been observed over many centuries in the form of natural magnets made of the mineral magnetite. A naturally magnetized piece of magnetite, when fashioned into the shape of a pointer and placed on water, could be used as a compass to indicate direction. This naturally occurring magnet was called lodestone, or leading stone. It is only in the last 150 years that magnetism and electricity have noticeably transformed our lives. In the 19th century, James Clerk Maxwell, born 1831, died in 1879, discovered the connection between electricity and magnetism. Maxwell, a Scottish scientist working in the field of mathematical physics, studied the effects of electricity, magnetism, and light energy. With a publication of A Dynamical Theory of the Electromagnetic Field in 1865, He explained how electric and magnetic energy travel through space as electromagnetic waves, moving at the speed of light. German-born theoretical physicist Albert Einstein, born 1879, died 1955, demonstrated a further astonishing property of electromagnetic energy when he proved the equivalence of energy and matter. This equivalence is expressed by Einstein's famous equation E equals mc squared that relates energy, or E, to mass, m, and the speed of light in a vacuum, c. This showed for the first time that matter can be thought of as a form of, quote, packaged energy, end quote, in a somewhat stable form. The makeup of an energy bundle, such as the individual atom, will determine the degree of its stability and how the atom will interact with other nearby matter and energy. Electromagnetic force makes this possible. The strong nuclear force is much less familiar to people, but also essential to the stability of the chemical elements. It makes it possible for particles in the nucleus of an atom to bind together. It operates over very small distances and at scales much smaller than our senses can detect. It establishes the rules for the behavior of the fundamental building blocks of matter. The most abundant element in the universe is hydrogen, estimated to make up 3/4 of all elemental matter. This simplest of all elements is composed of a single proton and a single electron. All other elements have more than one proton and require the presence of the strong nuclear force to permit multiple protons to remain bound close together within the nucleus. Since protons have a positive electric charge, they will normally repel each other when close together. However, at extremely close range, at a distance billions of times smaller than the thickness of a human hair, they will attract each other, due to the strong nuclear force. Without this force, there could not be any elements heavier than simple hydrogen, because 2 or more protons could not remain together in a nucleus. The weak nuclear force is involved in aspects of nuclear decay, the process whereby a nucleus changes by emitting either electromagnetic energy and or subatomic particles. It makes the nuclear fusion reaction in the sun possible. In many stars, including the sun, the temperature is extreme enough so that the protons and electrons no longer form elements such as hydrogen. Instead, the protons and electrons are freed from each other in a state known as plasma. These freely moving particles combine in various reactions that release electromagnetic energy, such as light. Much of the sun's light energy is produced through proton-proton fusion reactions. As mentioned previously, 2 positively charged protons will normally repel each other when in close proximity. Proton-proton fusion occurs in stars if the temperature, i.e. kinetic energy, or energy of motion of the protons, is high enough to overcome their mutual repulsion. The weak force, or interaction, permits one of the protons to lose its positive charge by releasing energy in the form of a positively charged particle that quickly combines with one of the many negatively charged free electrons within the sun. This results in a proton and neutron fusing together as one particle, along with the release of electromagnetic energy in the form of light. This new particle will fuse with another proton, resulting in yet another new particle along with the release of still more electromagnetic energy. Additional fusion reactions create still more particles and energy. Over time, the process converts the original hydrogen nuclei into other heavier nuclei, along with large amounts of electromagnetic energy traveling outward in all directions. This energy continuously radiates out from the sun and fuels life on Earth. All of this is only possible because of the precise nature of the 4 fundamental forces. Fun fact, the sun fuses 620 million metric tons of hydrogen in its core each second. In their book, The Grand Design, Stephen Hawking and Leonard Mlodinow state, quote, "By examining the model universes we generate when the theories of physics are altered in certain ways, one can study the effect of changes to physical law in a methodical manner. Such calculations show that a change of as little as 0.5% in the strength of the strong nuclear force or 4% in the electric force would destroy either nearly all carbon or all oxygen in every star, and hence the possibility of life as we know it. Also, most of the fundamental constants appearing in our theories appear fine-tuned in the sense that if they were altered by only modest amounts, the universe would be qualitatively different, and in many cases unsuitable for the development of life. For example, if protons were 0.2% heavier, they would decay into neutrons, destabilizing atoms. The expansion of the universe. Albert Einstein's general theory of relativity revealed that gravity occurring because of the presence of matter and energy will distort space and time. When Einstein developed this theory of gravity while working on the general theory of relativity, his equations showed that the universe should be either expanding or contracting. He and other scientists believed that the universe should instead be static, so he modified his original equations to allow for a static universe. Several years later, however, Edwin Hubble showed that the universe was indeed expanding. This interesting discovery is explained in more detail in Chapter 3. Measurements have shown that the rate of expansion of the universe is great enough so that matter in the universe will not collapse together from the effects of gravitational attraction. Fortunately for life on Earth, this property of the universe prevents everything, including the Milky Way galaxy, from a catastrophic collapse. Impossible coincidences. The physical properties of the universe, along with many fundamental physical constants, such as the universal gravitational constant from Newton's equation of gravity and the speed of light in a vacuum, have the precise values necessary for the universe to be stable and long-lasting. Somehow, the physical laws and properties are favorable for both the existence of fundamental elements and for the combination of these elements into various compounds through chemical bonds. Somehow, the universe also has precisely the right quantities to permit galaxies, stars, and planets to exist in great numbers and to persist over time. Amazingly, the universe is not only compound-friendly in this way, but bio-friendly as well. The properties that enable chemical elements and compounds to exist would not necessarily lead to an environment that was favorable to life as well. In fact, for the most part, the properties of the universe are overwhelmingly hostile to life. But we do know that life thrives on at least one planet, our own planet Earth. This bio-friendly nature of the universe is most surprising because it has no natural explanation. In fact, except for a number of factors that work together to benefit and favor life in the universe, there would be a universe full of chemistry, but empty of life. The universe not only has just the right properties to permit abundant galaxies, stars, and planets to persist over time, but it also has precisely what is needed for life to thrive on at least one planet. What's more, the conditions in some areas of the universe are suitable not only for simple forms of life, but for complex life forms as well. Consider the 7 notable aspects of the universe below. 1. The force of gravity is exactly what is needed to ensure the stability of galaxies, stars, and planets within star systems. 2. The rate of expansion of the universe is great enough that the force of gravity does not result in the collapse of all matter in the universe. 3. The strong nuclear force is exactly what is needed for nuclear fusion to result in a stable nucleus within an atom. 4. The weak nuclear force is exactly what is needed to allow successful radioactive decay of subatomic particles and to permit the ongoing hydrogen fusion process in the Sun and other stars. 5. The magnitude of the electromagnetic force is exactly what is needed to make possible the stability of the chemical elements that are the building blocks for all the visible matter found in the universe. 6. The number of spatial dimensions in physical space is exactly what is needed to allow stable orbits of planets to exist in the solar system. And 7. The masses of the proton, neutron, and electron are exactly what are needed to form stable chemical elements and the isotopes necessary for energy production from nuclear fusion in stars. An inquiring skeptic requires an explanation for why the universe has these properties that result in more than just the simplest possible form of matter, or just simply light energy, or even nothing at all. The requirements for life. Life can simply be defined as something that has the capacity for metabolism, growth, reaction to stimuli, and reproduction. For life to exist and thrive, certain environmental conditions must be met. The National Aeronautics and Space Administration, known as NASA, has published a document called the NASA Astrobiology Roadmap. They define primary habitability criteria for a planet, such as extended regions of liquid water, conditions favorable for the assembly of complex organic molecules, and energy sources to sustain metabolism. The one chemical compound mentioned by NASA as a necessary ingredient is liquid water. A water molecule has a relatively simple structure composed of 2 atoms of hydrogen bound together with 1 atom of oxygen, but it has some unusual properties. Unlike other compounds, it remains liquid over an unusually wide temperature range. The United States Geological Survey Water Science School states that water is unique in that it is the only natural substance that is found in all three physical states, liquid, solid, and gas, at the temperatures normally found on Earth. Water is liquid over a temperature range of about 100 degrees Celsius, from 0 to 100 degrees. For comparison, hydrogen itself is a liquid over a range of about 6 degrees, from minus 259 to minus 253 degrees Celsius. And oxygen is liquid over a range of about 36 degrees Celsius, from minus 219 to minus 183 degrees. Another common compound is carbon dioxide. It is liquid over a temperature range of about 21 degrees Celsius, from minus 78 to minus 57 degrees. The USGS Water Science School publication points out another special property of water. Quote, "Water is called the universal solvent because it dissolves more substances than any other liquid. This is important to every living thing on Earth. It means that wherever water goes, either through the air, the ground, or through our bodies, it takes along valuable chemicals, minerals, and nutrients." End quote. Perhaps the most amazing property of water is its behavior near its freezing point. Most substances are more dense as a solid than as liquid. Water is unusual in that its solid form, ice, is less dense than its liquid form. Liquid water shrinks as it cools until it reaches 4 degrees Celsius. Then it begins expanding. Because of this property, it is one of the very few materials that floats when in its solid form. Without this property, freezing rain, frozen snow, and ice would sink and accumulate in lakes and in the ocean depths. The oceans would freeze from the bottom up. For life to be sustained, there must be a persistent and sufficiently large energy source. The universe provides an energy supply for star systems, such as our own solar system, through radiant energy from the stars within those systems. This energy is supplied in the form of electromagnetic energy through the process of nuclear fusion. The following elements are necessary for life, simple or complex, to exist on a planet. First, an atmosphere to prevent extreme variation in temperature between night and day and to provide a shield of protection from incoming genetically destructive ultraviolet radiation. Light energy from the sun consists of visible light, but also low-energy infrared and high-energy ultraviolet radiation. The low-energy infrared radiation is not harmful to life on a planet, but exposure to the high-energy ultraviolet radiation will suppress the immune system, cause premature aging of the skin, damage the eyes, and even cause skin cancer. The predominant gases in Earth's atmosphere are nitrogen at 78% and oxygen at 21%. An important aspect of the upper atmosphere is the presence of ozone, also known as trioxygen, a molecule formed by the combination of 3 oxygen atoms. It is much less stable than the common form of oxygen composed of 2 oxygen atoms. The oxygen-rich atmosphere provides a layer of ozone, also called the ozone shield, as protection from dangerous ultraviolet radiation. Some ultraviolet radiation is absorbed by the nitrogen and the common form of oxygen in the atmosphere. However, some of the most dangerous ultraviolet radiation can only be adequately shielded by the ozone. In the ozone layer, the number of oxygen molecules of the common form is over 100,000 times the number of ozone molecules. Fortunately, there are enough of these scarcer ozone molecules to do the job of absorbing most of the dangerous ultraviolet radiation emanating from the sun. 6 elements are necessary for life. CHNOPS stands for the chemical abbreviations of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Combinations of these 6 elements make up most of the biological molecules on Earth. They make up almost 99% of the mass in the human body and are necessary for the existence of organic compounds. If any one of them were not present in the universe, or not stable over time, life as we know it could not exist. There must be a source of adequate energy, such as the radiant electromagnetic energy supplied by a star. The star must also have sufficient gravity to hold the planet in a stable orbit. Also, a large iron core supplies the iron with a magnetic field to protect it from radiation that would be deadly to life and would eventually strip away the atmosphere. A star such as the Sun emanates a constant stream of dangerous high-energy electrically charged particles known in our solar system as the solar wind. The movement of molten iron deep within the planet, such as Earth, creates electric currents that generate a protective magnetic field to shield against these particles. Through a complex process, the magnetic field breaks down and redirects the particles, so that only a small amount of the radiation penetrates the shield. Also, the rotation period of the planet must be great enough to create the necessary protective magnetic field. A moving electric charge will produce a magnetic field. To demonstrate this effect, we can make a simple electromagnet by wrapping a wire around an iron bar, then passing an alternating electric current through the wire. The motion of electrons in the wire will produce a magnetic field. An electromagnet like this will attract certain metals such as iron and nickel, but not other metals such as copper. A planet's magnetic field is created by swirling motions of liquid conducting materials such as iron in the planet's interior. If the interior of a planet is solid, or the speed of rotation is too slow, the magnetic field will be too weak to produce protection for the planet. A sufficient supply of liquid water on its surface is necessary, and the planetary orbit must be in what scientists have defined as a habitable zone within a star system. This requires that the planet be close enough to the star so that water will exist in a liquid form, but not so close as to destroy any protective atmosphere and boil away all the elements and compounds necessary for life. And finally, the planet's orbital motion needs to be nearly circular, so it's entirely within the habitable zone during its journey around the star. Some of these conditions, such as the energy source and protection from deadly cosmic radiation, are absolutely essential. The absence of one or more of the others would produce an environment unlikely to permit the existence of complex organic molecules. The fact that they are all permitted confirms the, quote, bio-friendly, end quote, nature of portions of the universe. Life would be impossible if the universe did not permit these conditions to exist. It cannot be concluded that Earth is unique in the universe, for there are many star systems similar to our own solar system that could support Earth-like planets. However, considering that many aspects of the universe that are unfavorable for life, it is remarkable that the conditions necessary to sustain life exist anywhere in the universe. The special bio-friendly nature of the universe is only possible because of the precise nature of the physical laws and properties of the universe. The preciseness of the characteristics of the universe is comparable in many respects to the isolated mountain meadow discovery described previously. Chapter 3 explores this further. From the form, structure, and setting, the only reasonable explanation is that the hikers found an intentionally constructed garden plot. There is no alternative explanation for the neat rows, or why so few of the native plants from the surrounding area are in the garden. They cannot conclude that they have simply come across a rare coincidence. The evidence clearly shows that someone had planned and planted a garden in that plot.